It's a big one on the paper, but hopefully I'll do it. So, good evening, everyone. So, let me introduce the speaker today, Professor Kuldeep Meel. And Professor Kuldeep Meel holds a Stephen Fleming Early Career Associate Professorship in the School of Computer Science and an Associate Professor at the University of Toronto. His research interests lie at the intersection of formal methods and artificial intelligence. He's a recipient of the 2022 ECP Early Career Research Award, the 2019 NRF Fellowship for AI, and was named AI's top 10 to watch by IEEE Intelligence Systems in 2020. His research program's recent recognitions include the 2023 CSCM Research Highlight Award, 2022 ACM Sigmund Research Highlight, IISc 2022 Early Career Spotlight, Distinguished Paper Award at CAB 23, Best Papers of CAB 2022-2020, Special Issue in FMSD Journal, Best Paper Award nominations in ICAD 21, Day 23, First Place in Model Counting Competition. Above all, Professor Meel is also passionate about teaching and is most proud of his recipient of University Level Annual Teaching Excellence Awards in 2022-23. Before moving to Toronto in 2023, he held NUS Presidential Young Professorship at Sung K Assistant Professorship in the School of Computing at the National University of Singapore. Before joining NUS in 2018, he received MS and PhD from Rice University, co-advised by Professor Supratik and Professor Moshe. His thesis work received the 2018 Ralph Budd Award for Best PhD Thesis in Engineering, 2014 Outstanding Master's Thesis Award from Vienna Center of Logic and Algorithms. He graduated with Bachelor's of Technology in Computer Science and Engineering from IIT Bombay. Lastly, and most impressively, Professor Meel has an algorithm named after him, the CVM algorithm, where M stands for Meel. None other than Professor Don Knuth praised it as their algorithm is not only interesting, it's extremely simple. Furthermore, it's wonderfully suited to teach students who are learning the basics of computer science. Indeed, ever since I saw it a few days ago, I have been unable to resist trying to explain the ideas to just everybody whom I meet. Therefore, I'm pretty sure that something like this will eventually become a standard textbook topic. Professor Meel, you're there to have today.
Thank you. Thanks a lot, Vivek, for the generous introduction. Thanks to Arindam for hosting me. So usually one gives a talk on in a line of work that is completed, but this is a line of work that I'll talk about based on these two papers, but I think this is a very early stages of what we are trying to do here. So this has been a collaboration with Saurabh Chakrabarty, who is at IISc Kolkata, Diptarka Chakrabarty, who is at National University of Singapore, Remy Delaney, who was my master's student, and Gunjan Kumar, who was postdoc co-advised at NUS, and now he's a faculty member at IIT Kanpur. So I want to talk about, I'm not a theory person per se, so I do formal methods. In particular, I built set solvers. So set is this NP hard problem, and we live in the world where NP stands for not a problem. So I come from the place where set is not a really scary problem to work with. So we have been working with these set solvers, and over the time, we have been figuring out that, well, we should take inspiration from what theory says about NP, and at times we have been feeling that it's unsatisfactory or needs some revision. So I'll talk about some perspective about how we can go about it. Okay. And in particular, I talk one crucial aspect that I'll talk about is what's the power of getting a satisfying assignment. Hopefully, this will become clear in a few slides. So if you want to develop a new theory about analyzing if you want to develop a new theory about analyzing algorithms that are implemented, so perhaps it's a good idea to first look at the past, how we went about developing theory of analysis of algorithms. And we'll go back all the way to 6 years ago when Knuth, who is considered the founding father of modern analysis of algorithms, where describes that why one should even analyze algorithms. And Knut gives two answers to this. One is that you encounter beauty of mathematical patterns. So hopefully any kind of analysis framework we develop should allow us to achieve the first end. And the second is that analysis allows you to gain practical benefits. Why so? Because you have a theory that can allow you to compare algorithms, and that if you improve a particular algorithm according to this theory, then it should lead to improved performance. So what was Knut's approach towards analyzing algorithms? Well, one way is that we had to specify the algorithm. The algorithms used to be, if you look at the papers from 50s and 60s, this would be a procedure, do these things. It wasn't clear how to analyze algorithms. You can write something very in 2 lines versus you write something in 10 lines. So from a natural language statement, you can try to write it formally. And then we had to analyze what are the operations that each of the statements entails. So for every operation, we analyze the cost. The way to come up with the cost is you look at the system, you see how much cost it takes to do certain operation. And we had to also look at the input models, and what kind of inputs are going to be given to this procedure. For every algorithm, you identify how. So now we have analyzed the basic operations. So now you look at the algorithm, you say, well, how many times I'm going to call this operation? So that's the frequency of. And the total runtime would be a summation over the number of times I call a particular frequency times the cost. And this would be a sum of all the operations. And what are the objectives? Well, for the mathematical beauty you can encounter in addition. For the second case, whatever analysis we come up with, it should allow us to predict the performance of the algorithm. Okay, so if I tell you that algorithm takes 8 n times and is some parameters, so if n increases, then I should see a linear behavior. And what it also should allow me to is to compare two algorithms. If I tell you one algorithm is 8n and another algorithm is 16n squared, then it should happen that when I run it, 8n is faster than 16n squared. And that should allow me to improve further, because I say, well, if I want to improve 8n, can I come up with something else that is 4n? And in that case, it improved. Okay, so these are the goals, how one should go about analyzing algorithms. And of course, as I mentioned, along the way, we hope that we'll encounter beauty of mathematical patterns. And this quickly led us to develop the theory about different classes of algorithms. Edmonds started to look at like what are efficient algorithms, which is what we call as polynomial time algorithms. Very soon we discovered that there are problems for which they exhibit a strange structure. Like it seems hard to come up with an algorithm to solve the problem, but once you have the solution, it seems easy to check them. And that was, of course, the problem of NP, non-deterministic polynomial time computations. And it turned out there was only not just one, there are many such problems, and a lot of them can be reduced to these problems. And then Stockmar said, well, there's an entire infinite hierarchy possible. So there's an entire polynomial hierarchy that was based on oracles. And that is like a rich theory that is based on oracles. But I would like to claim that for most part, especially, this is a more theoretical oriented audience, if you teach the theory based on oracles, then it's really like it's confined within the theoretical framework. You don't see it being applied so much outside the theory community. And why so? Well, for some sense, this is an entire theory that is based on, and the first class is the one that starts getting interesting is NP. And we thought NP is a very hard problem, so we didn't have any tools. So, this infinite hierarchy is going to remain in the theoretical framework. But that has changed, as I mentioned. In last 30 years, we have seen what's called the set revolution. Consider the canonical NP complete problem given a set of constraints, find an assignment that is so that the formula evaluates to true. And in this case, assigning all the variables true should make the formula evaluate to true. So what I changed, again, we can go again to Knut, who wrote an entire book on set solving. So this is an entire book about how to build set solvers. And what Knut says is that the current solvers can find solution to problems involving millions of variables, which were thought to be hopelessly difficult just about a few years ago. Okay, so these are, as I speak, these solvers are being applied in all the companies out there. They are running millions of CPU, hundreds of thousands of cores on these CPUs, trying to do verification, using e-commerce and so on. So what happened? As solvers became easy, so in late 2000s, we said that now that set is easy. And I do want to put easy in quotation. I don't mean to claim that it's easy for every problem out there, but it turns out to be easy for problems that arise from practice. So it was time to look beyond satisfiability. And that led to development of algorithmic frameworks for problems such as optimization, counting, sampling, and synthesis. I'll touch upon these two problems in the rest of the talk on counting and sampling. I'll define them formally soon. It should be late 2010s. Now that I think it's about the right time to start thinking that now that these solvers are actually being used as oracles, it should be a time to have a theory that is based on the set oracle. Yeah, so what is the set oracle? Yeah. Yes.
So, but how do you sort of differentiate between, like, is it the scale? Is it the fact that that solvers tend to be larger, or
No, I mean, these are different problems, and all of these, in general, for the constraint set of constraints, for different kind of constraints, we have seen a lot of progress. I'll focus trying to develop theory for the set solvers, but most of the things I'll talk about do apply to the other constraint solvers, like integer linear programming, mixed integer linear programming solvers.
but I should not view this as at a very coarse level that because of polytime reductions, all NP-complete problems are the same. Hence, SAT is like, the fact
No, no.
that SAT being solved is not a statement that I can't solve, let's say, large independent set problems. Like there are again like cryptographic problems that are.
Yeah, that's why I did mention this easy in quotations. It arises from the problem that arises in.
So does it mean practice the SAT problem structure for it it's easy, but in general, what if it's hard?
That is, of course, remains the case. We don't know a polynomial time algorithm, but for everything that works, of course, it's polynomial time because it runs in a fixed amount of time.
Practice there is some structure. Like in linear program, this smooth analysis is there. You know, okay, slightly perturbed, it becomes probably an easier problem to solve. In SAT, it's not really that, but some kind of practical structures are there for which it is easier.
Yeah. So some kind of structure that a big open problem is, of course, trying to identify what that structure is. There's some progress in past few years. And for this kind of structure, the kind of algorithm we have designed seems to do very well. Even though those are still, in the worst case, can take exponential amount of time.
Probably like kind of, in fact, orthogonal to the point you're trying to do. But are there settings where they remain Achilles heel for SAT solvers?
Yes. I mean, of course, like pigeonhole principles are hard for one kind of algorithms.
Yeah.
Over the years, we have figured out to look for pigeonhole structure and solve it differently.
Yeah.
So there are, of course, problems out there that are still very hard for the set solvers. And in last year, there has been a very rich theory being developed that tries to capture the power using the proof systems on which the solvers are working. So you can come up with a problem that is exponential size, from the proof system, so no solver has a chance of solving it. So yes, we do. We can identify synthetic instances that are hard. It just doesn't figure out how, why they don't show up so often in practice. And so it's still a big problem in trying to figure out how to reason about in practice. But what I'll talk about is now that we have set solvers, how to build theory beyond it. But of course, there's a lot of work that needs to be done in understanding these solvers. Right. So, I've been talking about oracles and solvers. So let's try to define formulas. So I'll focus in case of Boolean formulas, but most of the things I talk about will apply to general languages in NP. Okay. But in case of Boolean formulas, the view of an NP oracle is that it should return yes if the formula is satisfiable and no if it's not satisfiable. What does the set solver do if you give a solver? Well, it returns a satisfying assignment if formula is satisfiable and returns no otherwise. There's also aspect of timeout that I'm going to ignore for now. But again, needs to be more theory, more work needs to be done to understand timeout behavior. So, but for now, let's think of a solver that is going to return a satisfying assignment when the formula is satisfiable and returns no otherwise. The solvers also return proof of unsatisfiability. So they don't only just say it's unsatisfiable, they actually give you a proof why it is unsatisfiable. But for now, we are also going to ignore that. So, if you want to model an oracle that can capture the behavior of the solvers, I'm going to model the oracle saying that I have an oracle. Here, we are not going to deal with timeout. So we'll say that it returns a satisfying assignment if formula is satisfiable, otherwise no. Okay, no proof here. The oracle will just return a satisfying assignment, otherwise no. So something that I do want to claim that every kind of solver that is out there that can handle constraints has a similar behavior. When the set of constraints is satisfiable, it gives you a witness. Any algorithm that has been implemented, a tool that you can download, compile, and run, if it's solving a set of constraints in any general language that you care about, it will give you a satisfying assignment when this set of constraints are satisfied. Okay. So these are constructive in this way. They give you a witness that why the formula is satisfied. Of course, there are algorithms out there that that are non-constructive, but we don't know how to actually implement and make them work in practice. So since we are going to keep coming back to the notion of satisfying assignment, I do want to claim that this is capturing what is out there in general, not just restricted to the set one.
But you don't want to rely on something like self-reducibility here.
Let's come to that. So, all right. So, I'm saying, well, what are you talking about? This is what we often teach in undergraduate. There's not a big difference between a decision and the search problems. Can't you just simulate the set oracle by making n calls to NP oracle? So what's the big deal? Well, I mean, there are problems. Look, like I give a formula, if you want to find a satisfying assignment, you can make n calls to NP oracle, do self-reducibility, which kind of holds true for almost all interesting problems out there, get a satisfying assignment. But I want to say that, look, even for this problem, set oracle will take one call. So there is a difference of n. Say, what's the big deal about? It's only a factor of n. Oh, you say, well, is the formula satisfiable if x1 is 0? First, you say, is the formula satisfiable? Yes. Is the formula satisfiable if x1 is 0? The answer is yes. Then you say, okay. Is it satisfiable if x1 0 and x2 is 0? No. Then you know that it must be x1 should be 0, x2 should be 1, and so on. So you'll at least be able to go along one path. You can even use it to enumerate solutions. So let's say x1 is 0 and it's unsatisfiable, but formula is satisfiable, so x1 must be 1. x1 1, x2 should be either 0 or 1. If I set x2 to 0, if the formula is satisfiable, then it's okay. I can find some assignment. So you can make n calls. Well, it's just a factor of n. It's not really just a factor of n. That is the difference between the solvers from 90s and today. You take a million variable formula, if it's million times slower, you won't be talking about set solvers. Knut won't be writing a book on set solving. If you want to convince yourself why this million factor is big, slow down your internet by a factor of million and see how often you will check Google. Not a factor of n that we can ignore. This is the factor that matters. So if you have an algorithm that takes O of n time versus O of 1 is what you care about. So there are problems where one would take O of n, the other one would take O of 1. We would care about, like we will say O of 1 is the right complexity. So what we need is a fine-grained analysis that tells us we can't just simply say, oh, let's look at every analysis that we have done for NP Oracle, and there would be only a factor of n. Perhaps we can ignore it. It can be up or down. We can ignore it. That's not the case. And in fact, it's not also the case that there will always be a factor of n. Why so? Let's say I want a problem. I'm going to consider a very simple example. I just want to know is it satisfiable. It takes one call in both cases. So there are problems where there's a factor of n. There are problems where there's no difference between set and NP Oracle. So we should understand where the difference is. What are the problems where NP Oracle takes more time versus set Oracle? And why we should do this is exactly why we care about analysis of algorithms. The complexity should allow us to predict the performance. You look at the complexity, should allow us to tell what would happen if I implement this algorithm. And it should also give us guideline that if I were to improve the algorithm with respect to this complexity, it should manifest in practice. And the message that I want to drive home is that, look, we should do the algorithm analysis based on oracles that can capture the physical reality. The physical reality is that the set solvers are out there. They always give a satisfying assignment. So we need to have a theory based on this, so a model that can capture their behavior. So I'm going to talk about this, illustrate these aspects about algorithm performance improvement comparison with respect to two problems. So these two problems are sampling and counting. In case of sampling, you are given a Boolean formula. You are interested in sampling every solution with equal probability. We want to allow some slack, so we'll also allow a parameter epsilon. We want to sample solutions which are within probability 1 plus epsilon factor. In case of counting, we are interested in counting the number of solutions of the formula. But again, we allow some slack. So you have parameter epsilon delta. So we want to compute an estimate which is within 1 plus epsilon factor with confidence at least 1 minus delta. Throughout the talk, I'm going to assume epsilon to be constant. A lot of these things carry over for arbitrary epsilon, but things will become too messy otherwise. Okay, so these are the two problems with which we are going to study. What is the power of satisfying assignment? In what case having a solver satisfying assignment helps or not?
But you're saying earlier the SAT solvers out there are even more powerful.
Yes.
In the sense that they also give certificate of. So has that thread been explored?
No, that's something I think would be an interesting line to pursue. Yeah. So as as I mentioned, I just want to talk about some of the results which I think are very exciting, and we are at the early stages. The field is completely open, so we have barely scratched the surface. Okay, so we'll start with counting, and so there's an interreducibility between sampling and counting. What does it say? It says that you can take a counter and you can get a sampler. Okay, and we can implement a model counter by making log n times log 1 by delta NP Oracle calls. Okay, so if you have NP Oracle access, this is a classical result by Stockmeyer. So one of the first algorithms for doing sampling is based on exploiting interreducibility. What is the algorithm? Well, we have to decide whether to assign x1 to 1 or not. So you assign x1 to 1 with the probability of the number of solutions where x1 is true over all the solutions. Once you assign x1 to 1, you now can assign x2 to 1 proportional to the probability where x1 and x2 both are 1 over the total number of solutions where x1 is 1. And this way you can assign, you can slowly construct a sample. So what's the complexity of this algorithm? This is a classical algorithm by Jerome Valentin and Vajrani. What is the complexity of this algorithm? So it turns out in the complexity analysis, for some union bounds, you will have to set delta to be 1 by 2 to the n. Okay. So what is the complexity of this algorithm? Let's look at with respect to NP oracle. So we have to make n calls. Each of the calls to the counter will require delta to be 1 by 2 to the n. So that becomes n log n calls to the NP oracle. So the complexity with respect to NP oracle is n square log n. Turns out you can't use satisfying assignment, power of satisfying assignment here. So the complexity of with respect to set oracle is n square log. So this is an algorithm that's actually not able to use the power of set oracle. Even though you get a satisfying assignment, you don't get much out.
Can you go through the n square thing? And so you're setting
Yeah.
one, it's like you're drawing from the marginals iteratively.
Yeah.
This is the marginal of x1.
Yeah.
To do that, you'll have to log in NP oracle calls.
No, you do. Yeah, exactly. And log n calls because there is
So
some.
delta is 2 to the n.
Yeah,
Okay.
there is some.
I see. Yes. So that n is coming from delta and the
Yeah.
other n because you have n variables.
Exactly. Yeah. So that n square log n calls in. So this is where we wanted, like, if you are developing a theory, we have the oracle model. So you ask, like, hey, the algorithm was initially really designed with respect to NP oracle, as taking as a viewpoint. Now that I set oracle, maybe there's a different design of algorithm that can exploit the power of set oracle. Maybe I can think about designing algorithm in a different way, where I can exploit the power of set oracle, where I can get the satisfying assignment. So let me tell you. So is it possible that we can get an algorithm with a better complexity, perhaps with respect to the set oracle? And turns out, yes. And you had to design a very different algorithm. So how does this algorithm work? If you imagine this blue circle to be the space of all possible assignments, the dots are satisfying assignments. And you can partition the space of solutions into cells that are roughly equal. And in that case, you can go and pick a random cell. If the cells are small enough, small enough by which I mean the number of solutions in the cell is not too much, you can enumerate all the solutions and pick one of the solutions. Of course, for all of this to work, we need the way of being able to partition into roughly equal small cells without knowing the distribution. Turns out this is possible using 3-wise independent hash functions, which can be implemented using XORs, which can be done very well by the set solvers out there. How many cells do we have to partition into? Well, what is the definition of small? So we'll say cell is small if it is about 200 solutions. So how many solutions we need to divide in? We want all the cells to be about 200 solutions. So we should divide into the number of cells is the number of solutions over threshold. How can we get this estimate of the number of solutions? Well, we can invoke an approximate model counter. So we do one query to the approximate model counter. We figure out how many cells to divide into. We use XORs, we partition them, pick one of the cells, enumerate the solutions, pick a solution that we enumerate. So the complexity is we had to make one call to the counter, followed by enumeration of threshold many solutions. So what is the complexity with respect to these oracles? So making one call, here the delta is just a constant. You make log n calls to the NP oracle. Plus, what's the complexity to enumerate solutions? How do you enumerate? You find one, you block it. You say, give me another solution, but not this one. And give me another solution, but not this one. So you have to make n times threshold many queries. Threshold is a constant here, so n times threshold is n. So from the perspective of NP oracle, we have to make log n plus n queries. In case of set oracle, you make log n queries to get the count, and enumeration, every query is just order 1. So the complexity is of log n. Well, okay. I mean, now we have algorithm. That algorithm seems to have much better query complexity with respect to set oracle.
Like when you're dividing it into these cells,
Yeah.
How are you enumerating? Like that too is.
So you divide by writing a hash function, then you pick a cell randomly. Now that becomes a set of XORs that you have to solve.
So the hash function does allow you to somehow enumerate.
No. You use a set solver to enumerate. So.
Oh, I see. We have a constraint that says that you're only looking at solutions within that cell.
Yeah. You say I had divided into n cells. I just want to, and this is the formula you give to the solver.
The blow isn't bad, like in the sense that the number of variables still remains linear.
Yes, because we know how to do certain encoding, and of course, this is what we have spent 4 or 5 years making it faster, but it works in practice. All right, so okay, now I talked about 2 algorithms. What was the first algorithm? The complexity of it couldn't use a satisfying assignment in any way, so the complexity was n square log n for both NP oracle and the set oracle. What was the complexity for the second algorithm? It was n plus log n for NP oracle and it's log n for the set oracle. So we indeed got an algorithm that has much better complexity with respect to set oracle. Yeah. So we got an algorithm that is much better. So one, having an oracle changes the perspective. You design different algorithm that can achieve significant improved complexity. That's, yeah. It only makes one call to the counter. Log n. A counter can be done with log n calls. Okay, now that we had 2 algorithms, remember, I mean, why we ever do an analysis of algorithm? They should allow us to predict what would happen when you run them. Okay. So let's say NP Oracle was the right model to analyze algorithms. And you implemented both of these algorithms. How do you think like the algorithms would behave in practice? They would behave like there were one that would look like n squared, the other one would look like n. Suppose set oracle was the right model to analyze complexity. How would they behave? Deepak just got in time. So if set oracle was was the right model, then they would behave as exponentially apart. So let's implement them. So these are the benchmarks. These are the number of variables. This is the JVV that times out after, I think, 3,600 seconds. And here the unisample. This is the amount it takes to get one sample. What does this behavior look like? Is it like n square versus n, or is it like exponential gap? Exponential gap. So this model, if we analyze the algorithm with respect to this model, it allows us to predict what we are going to see in practice. So not only it allows us to design different kind of algorithm, it also allows us to predict what we are going to see. So if you want to put more effort in trying to come up with an algorithm with improved complexity, it would make sense that you start measuring the complexity with respect to set oracle. So that you can, if you improve the complexity, hopefully you will see it in practice. So this is a case where designing algorithm with respect to set oracle with improved complexity also manifests in practice. So what it allowed us to do is that it allowed the set oracle captures the algorithm performance. It allows us to compare algorithms, and having the model out there allowed us enable design of a different algorithm that was really designed to take the satisfying assignment, power of satisfying assignment. So that's the first part where analyzing complexity with respect to set oracle changes your perspective, you design different algorithms, and also you are actually able to predict what happens when you implement these algorithms. And this is also the case where we went from n to log n. So it also we could see this difference. And as you might also notice that the difference here is not n, it's a factor is n by log n. So, the gap is somewhere between n to 1, and it matters for different problems. So we need to explore for what problems, what's the gap between NP oracle and set oracle. And you design the algorithm with respect to set oracle, you analyze it with respect to set oracle, it tells you what to expect in practice.
I think lower bounds as well in this oracles.
So for this we don't have, but let's talk about another problem for which we can focus on the lower bound. And that will be the problem for counting. So given a formula, we are interested in count, estimate a count within 1 plus epsilon factor with confidence at least 1 minus delta. Of course, this is NP hard, so one has to perform computations with respect to NP oracle. This is what Stockmeyer faced with in 1983. So Stockmeyer had to figure out, well, how do I model this computation with respect to NP oracle? And this was if with a view, with a perspective of 40 years from Stockmeyer's model, this was amazing that Stockmeyer got it exactly right. So what Stockmeyer proposed is that, look, the way the algorithm should work is that you are given an initial formula phi, you have a formula psi. The counter can give another formula psi to the oracle. And the oracle is going to tell you, is phi and psi satisfiable or not? So what oracle will tell you is phi and psi satisfiable or not. And the queries can be adaptive. You can choose size as you go along. What is amazing is like all the approximate counting techniques that have been implemented use this framework. This is how all the approximate counters work. In practice that are implemented out there, you make multiple psi. You come up with different size, and what you want to do is, of course, you adapt them. You want to minimize the queries you make to the oracle. Okay, so this is the model Stockmeyer proposed, because otherwise the issue is that how do you deal with a problem that itself is NP, so you need some interaction mechanism, and this was the interaction mechanism. So, with the model, what's the lower bound? And it turns out Stockmeyer in his paper struggled a bit to prove it, but with Yao's MI, this is very obvious that this should be log n. Let me tell you without thinking about probability. So suppose every time you make different queries, finally return with an answer. Let's say we are interested in an answer that is a constant factor. Okay, epsilon is constant for us. So there are n possible answers. It's a binary tree. So at every point you can make 1 or 2 choices. So you must get log n. You have to do log n queries. And it turns out Stockmeyer also proposed the algorithm as upper bound. So not only necessary, but also sufficient. However, the algorithm that Stockmeyer proposed for upper bound wasn't actually a practical algorithm. So over a decade, we have worked on designing an algorithm that turned out to be very practical. And for a long time, we struggled whenever we would analyze the complexity of this algorithm. It was n log n. Then when we analyze the complexity with respect to set oracle, it turns out to be log n. For a long time, you say, well, yeah, things may be different in theory. It's n log n, but practice somehow n log n is better than log n. But if you analyze the complexity with respect to set oracle, it is log n. And why is this difference between n log n versus n? Because the algorithm makes this kind of query. Is the number of solutions less than threshold? In NP oracle model is n times threshold, and set oracle model is threshold. So one thing that was satisfying is that the set oracle, looking at the set oracle and trying to design an algorithm with respect to set oracle, actually leads to a better algorithm in practice. Because if you are designing an algorithm with respect to NP oracle, the strategy seems to be that, look, we think O notation is a good notation. So from O of log n, should we go and design a O of n log n algorithm? Not really, like that would be crazy. Why would you design a worse algorithm? It is indeed possible that you design two algorithms and they have both O of log n and one works better in practice.
Lower bound of Stockmar or that decision tree lower bound is for the NP oracle,
Yes.
not the sample.
Exactly. I'll come to that. They say that they follow Stockmar's model, these techniques, but they don't. There's a crucial difference. They actually you call a set solver. Remember, there are no NP solvers out there. There are set solvers. So they always call a set solver. So we need a natural extension of the model that should enable us a set oracle. So what they do, all the methods do, they give a formula and you get a satisfying assignment or unset. And they always call us, set solver in our model will replace it with a set oracle. That actually gets us to questions about, well, how many queries are necessary? Look, everything that is an upper bound for NP oracle is also an upper bound for set oracle. But of course, lower bounds may not necessarily imply. And the question is also, at least for us, it was just beyond pure curiosity, because for a long time we struggled that we get this satisfying assignment out of the formula. Can we make some use of it? Can we make some intelligent use of it? Like it's telling us something about the formula. And finally, we got a negative answer that no, you actually need log n queries. You can't make use of this satisfying assignment. Even though you get a satisfying assignment, you can't make use of this. And it turns out, of course, if you just try to use Stockmar's model, the lower bounds don't carry over because when it is satisfiable, you can get many, there can be exponential many solutions. So this is not a decision, a binary decision tree. None of the bounds work.
The formula is log n by log n.
Yeah, so that there is still a factor that would be nice to remove. So how do we, how can we prove the bound? So I'm going to give a brief sketch of the argument. Of course, it will be hard to go over everything, but just to say that there are interesting ideas, the other aspect about Knuths that you can discover interesting mathematical patterns in this oracle model. So what we do is that we have to focus on a slightly stronger oracle, which also promises that I'm not just returning an arbitrary satisfying assignment, I can even promise you that a uniform satisfying assignment. Okay. And the way argument works is that first we focus on, in order to do a lower bound, we focus on a restricted class of counters, which we call as semi-oblivious counters. And we show the bound for semi-oblivious counters, and then we say, look, the semi-oblivious counters and the general model are roughly equally powerful. So what is the general counter in general? You give a satisfying, you give a formula, it gives a satisfying assignment if it is satisfiable. We have to weaken this side, so we are going to say that, well, now you actually don't return me a satisfying assignment, but all you return is that, is this satisfying assignment equal to any of the previous satisfying assignments for every assignment so far? So what you return is that for sigma I, you say, hey, I can tell you whether sigma is same as sigma 1. So it will be one bit to tell whether it's same assignment as sigma 1. Second bit will tell is it's the same as sigma 2. Third bit will tell is it's same as sigma 3. So you'll get a vector. So at ith point, you'll get a vector that will be of size I. And of course, there are, for each of them, it can be either or equal. So there are 2 into I minus 1 possibilities for each stage. So what does this do? Like pictorially, you make these queries. And let's say these were the satisfying assignments where sigma 1 and sigma 2 were the same. So all you get to know is that look, sigma 1 and sigma 2 are same, sigma 3, sigma 4 are different. Okay? And you make this query, they are usually adaptive overlap with each other. So of course, this is much weaker. Like instead of getting a satisfying assignment, all you know is that whether they are equal to the previous or not. But what happens now? The degree is at most 2q if you are going to make 2q queries. We are making q queries. So now using the same argument, we need the number of leaves to be at least n. So we are able to get square root log n more. And now I'm going to tell you that, look, we'll run out of time. So because you have to struggle a bit more, not too much, using funnel inequality, it kind of, you can improve this square root log n to log n. This is for the semi-oblivious counter. We had also said that this counter can simulate a general counter. Once we prove that, we can show that this actually makes log n queries. Do want to tell you that there is an interesting idea about how to argue that you can simulate. So what you want to say is that, look, you look at two different histories. So as long as you have done this labeling, whether they are same or not. And look, this formula is chosen from, so consider all the formulas that have the same number of satisfying assignments. So you chose one of the formulas. You get, for one formula, you get one history. For another formula, you get another history. But let's say the histories are similar, like in the sense like sigma 1, sigma 2 are the same. So then there is a mapping between these formulas so that you don't gain much information about which of the formulas are out there. So really, like, you can't gain much because you don't, even if you look at the satisfying assignment, you don't know which formula you are working with. So there's a very little information that gets revealed. Even though you look at the satisfying assignment, you don't know what formula it is. So there's a very little information that gets revealed. And in this space of formulas, essentially the idea is that there are many formulas out there which have a similar structures. So even if I gave you the satisfying assignment, you don't know which one it is. So you can't gain much about the formula. There are many formulas among the space of all formulas with the same number of satisfying assignment. You can get the same behavior. So it doesn't matter which satisfying, what are the identities of the satisfying assignments. Okay, so to recap, there are two aspects that I want to mention about counting. One was that the algorithm that was out there for O of log n got a it didn't lend itself to a practical method. So you wanted to design another algorithm. And if we started designing algorithm with respect to NP oracle, you would end up with an n log n algorithm, very unsatisfactory state of affairs where n log n beats log n in practice. But actually, the algorithm is log n if you consider the set oracle model. And it also turns out that here's a problem where getting satisfying assignment is not really powerful. The algorithm could not exploit in any way, even though for years we also tried it heuristically. Look at satisfying assignment, make some guesses, some branching, all kind of ideas. We have never been able to make it work in practice. Not from just the complexity analysis, not even getting some speed up in practice. And it turns out this is a problem where you can't do better even in theory, as well as it turns out all the efforts in practice. So there are problems where getting satisfying assignment does not help. And there are problems where getting satisfying assignment helps. Of course, we have looked at two such problems of sampling and counting. And one thing again to highlight, like, look, once you start designing lower bound, there are new technical challenges. You can't just reuse the existing theory that has been built for NP oracle, which all crucially relies on this decision aspect because these are decision problems. So this also lends itself to very interesting technical challenges. So if that's the only thing that motivates you, then also there is more to do here. And of course, as I mentioned, it makes no sense to do analysis for oracles that have not manifested in practice and ignore oracles that are capturing the physical reality. The solvers are out there. You can download them anytime you want. So as I mentioned, these are just two problems I talked about. There's an entire polynomial hierarchy that is out there to explore. And here's a problem that I think would be very interesting to target, which is max set. You give an unsatisfiable formula, and you want to know what's the maximum number of clauses that can be satisfied. We know that log n calls to NP-oracle are necessary and sufficient. The necessary argument again goes by the decision tree, that you get one or two answers. What happens if there is a set oracle? So usually, if you think about the textbook algorithm for max set is, you say, well, is it possible I can satisfy half of the clauses? If no, can I satisfy n by 4 of the clauses? Or m by 4 if m is the number of clauses. And yes, then you can actually get a satisfying assignment. Maybe that can tell you what query to do. And then I would say that this is not just mere curiosity. Because the existing max set solvers, they actually use set solvers. In fact, the existing solvers also use sets. They also use the proofs generated by the set solver. So it will be nice to also look into that aspect. So they use set solvers. So it would be nice for us to figure out that if this usage, does it really matter? There are many possible algorithms out there for max set solvers. This is a well-established field in developing real max set solvers. Max set is also not just a theoretical problem. There are solvers out there. You can download them. They run. They can handle large problems. So these solvers use set solvers. So the right model is, of course, analysis with respect to set oracle. And if we can improve the complexity, then there's also a chance that this can lead to runtime performance improvement because we'll be able to figure out how to use satisfying assignments. So once we go beyond, what's the relationship between the classes that make one call to set oracle versus log n calls to set oracle versus linear many calls to set oracle? But this is again a well-established relationship in the context of NP. And none of those results again imply. What is the class relationship between these complexity classes? And as I mentioned, so far we haven't looked as we are restricting ourselves to the notion where the oracles are not providing proof, like they say no, but the oracles actually provide proof. So given a proof, what can you do? What can you change about the algorithm? The proofs are heavily used in all most of the formal method techniques. Like you take the proof, and based on that, you make subsequent queries. We can also look at a restricted model where instead of the proof, what is called a core. If you give unsatisfiable formula, it tells you a subset of clauses that itself are unsatisfiable. So what can you use from this information? All right. So, as I keep hammering the point, we do need the analysis. We had barely started. We need a lot of people to be working on it. So hopefully this talk gets you excited to look at these questions. With that, I'll conclude my talk. Thanks for being a wonderful audience this evening.
Into how to even further strengthen SAT oracles. Things like if they actually not only gave me, so one thing you said was let's say assume they give you a formulate random assignment, but like maybe like a median assignment. So among all the assignments, it gives you literally the middle. I'm just wondering if the feedback loop actually also goes in the other direction. Like using these oracles, now you're saying that, oh, if you were to strengthen the oracle like a bit for me, I could go even much further, let's say in MaxArt or something of that kind.
Yeah, I think it's a very good question. So it's a bit hard to see like we asked, like, oh, maybe we should modify the existing algorithm to return some solution.
Yeah.
So it's hard to see what how we can go about in modifying in case of CDCL in satisfying assignment, but we can. It's perhaps more interesting to do in case of unsatisfiable. So when it's unsatisfiable formula, then a subset of clauses are unsatisfiable, and we know there are many cores, and those we also kind of know how to, make the solver go in different direction. So and over the years, yeah, I mean, there are lots of algorithms out there where it is often observed empirically that some cores are better than other cores. But there's no methodological study that can tell us which cores are better or how you can. So, yeah, if you say that, look, in case of if we strengthen where it provides a core, maybe not the entire proof, but if you figure out that what are the properties of cores that make it better for algorithms, then it's also possible to go back and modify the solver too. In case of satisfying assignment, it looks harder. We are kind of in some ways limited by constrained by the whims of CDCL algorithm, and we don't.
It's a black box.
Yeah, so core finding is the algorithm runs and you do something more, and that algorithm is much more simpler, so we can do something. The forward pass getting the first assignment, we don't know what it. Yeah, so I think that would be something. But yeah, if you can figure out like what is the information that can be helpful, that's again like if you figure out this information is helpful in theory, then there's also motivation to build for practice, right? Or at least try out. You say, let me try out modulo this cost. If it improves, then I'll also improve the cost of funding that. So we don't know. Maybe like if you say that median assignment helps, maybe we change our heuristic to maybe not get median, but somewhere there. Yeah. So right now we don't seem to know that what even helps. Like it looks like so it. So, but as you see, like in case of sampling, getting one, anyone helps. In case of counting, we know that if you just give me uniformly one, so it doesn't have to be adversarial. You can say that, look, you have to just give me any of them. It doesn't help. But can it be made cooperative, like in the sense, like give me one that I can gain more information? And we don't know what that even looks like.
Anatomical model gives you a way of getting a good complexity of the problem.
Yeah.
I mean, maybe it just happens that for a couple of algorithms, a couple of problems that coincide. Does one need to do more? Look at more problems to see whether it.
Yeah, definitely. I mean, this is a claim based on two problems. Yeah, I think definitely. I mean, based on maybe three problems, getting a satisfying assignment is really order one cost. It's not n. No matter how large the formula, it looks like you just need one call. So, yeah, but I think I mean understanding it because like MaxSet, we do use satisfying assignment. We do use the core definitely. Like satisfying assignment depends on which MaxSet solver style you are building, but we do use the core, and we don't know how to even reason about it. Like the theory just say that it's yes or no, but actually, if you stop just to get like if you say that no solver can return the core, a lot of max solvers won't be able to work. Like they crucially rely on giving some small subset that comes from the proof and then tune the guide the heuristic in that way. So we do use it, but what is interesting is how we go about reasoning about it. And every other problem that is in, we can start with the problems where you are making polynomially many calls to NP oracle, where you say, well, what happens? I make set calls and then go beyond and attack general problems. Of course, there's another view because there are QBF solvers out there that can take the quantifiers and that can take, two QBF solvers that can take formulas of the type exist for all or for all exist. And in that case, you can say, well, they are going to give me a witness. Witness there looks like a tree or a succinct formula. And you ask the similar questions for things where you are going to make polynomial many equals to sigma to p oracle, pi to p oracle, polynomial many equals to QBF solver. So the one thing that I just want to mention there, I think that in reality, we don't have decision oracles. It doesn't say yes or no. It always gives more information. We should be able to model it.
Also interesting to not just go upwards or inwards. That is, look at problems like that are, and this is like finely in complexity. So flow problems that have a quadratic running, so poly, but n to the or a cubic running time, and then show that look, if I have faith in my SAT solver, I can actually do it in sub. So it's like from a complexity theoretic perspective, it's heresy. I'm using an NP oracle to solve a P problem. But if you're looking at that level of fineness,
Like if you teach an ETH harder, then you find in complexity.
yeah. But for hardness, I'm saying look at like a
Yeah.
like oracle. And so my faith is that this oracle is magically efficient. And so now I have a problem that a standard like a Ford Fulkerson uses n cube time. But if I have a stat oracle, I can actually do it in like n log n time with like access to the stat oracle.
That can be interesting because here you do get the satisfying assignment. So asking that what's the power if you get, because I mean, I think that's one thing that I really want to emphasize, that like the real difference between this algorithm and the next algorithm, I mean, sure, there is also difference in, but it just comes from this perspective that in one case you'll get the satisfying assignment. In one case, you go bit by bit because you don't get the satisfying assignment. So that's the change of perspective. It says, look, if I can get satisfying assignment, I can do more things. So yeah, this perspective maybe can also be used in other settings. Yeah, that is for a randomized. Yeah. NP oracle. I mean, sufficient, we know even off log calls are sufficient because everything that a NP oracle can do can be. Oh, off one call. Yeah, that I think one should be able to. I guess that's it. I think we could possibly some argument to.
Output itself is like log n, right? Like number of it should be like log n should be ruled out information theory.
But look, like the output of the solver is an n bit. Yeah, so yeah. I have to think. There was something we thought once, and it looked like you, but I don't know on top. Yeah, it would be. I mean, this is a problem out there. We have max set solver. They use set solvers. Can you tell what to expect? Yeah.
Advanced study and tools are.
I mean, the model does hold for not It holds for linear integer linear programming LP solvers and out there, right? Because they also give a witness.
So also, if you have
Yeah, at least for the NP hard one, they always give a witness. And also for free. I mean, I guess I don't know. I think if you know how the solvers work, but I also want to emphasize the witness just comes for free. The solver constructs the witness as it goes along. The cost to output the witness is writing on the terminal. And that is 1 over, something like 10,000. Okay. So the witness is truly for free. In fact, modern solvers, it will be hard to tell them not to output it. Okay. You'll have to change way more code not to output it. So, and then I think witness comes for free in definitely Cplex like every. They know it. I mean, they also know because branch and bound, you know that this is what you came, the trail gives you. They also don't work hard, like just like the set solver, like you just read it and you output it. So it does come for free. So as I made the claim, and I don't think you can download anything which say it's satisfiable, but I don't know why. Or at least it's constraint solving problems, right? So also for the CP solvers, I mean, CP solvers are very similar, right? You make decisions and the trail, when you say yes, you know it is yes. Yeah, in fact, the way these decision processes are designed, unless you assign all of them, you can't even be sure that it is satisfying assignment. So unless you construct the satisfying assignment, there was a change of philosophy in the modern solvers. So the modern solvers are designed in a way that until you assign all of them, the solver can't be sure that it's satisfying. So it has to assign all of them. And same for CP. Yeah. Thank you.
Okay. So this will be here tomorrow. If you want to do it in the campaign, well, I'll get an email to clinic.